Assalamualaikum and very good day to everyone. Our team name is Reactioners and our teammates are Jihin, Cheng Mao, Afif, Shahni and Minabiha. Assalamualaikum and very good day to everyone. For this project, our group choose methanol that produced from carbon capture utilization, the reaction between carbon dioxide and hydrogen to produce methanol and water. Moving on to our objective, we actually want to design a process for producing methanol by utilizing carbon dioxide and hydrogen. We want to demonstrate waste to wealth concept and promoting sustainable chemical engineering solution. Why we choose carbon dioxide as our main reactant? Because we can get carbon dioxide easily from greenhouse emission, global carbon neutrality goals, and readily available. So there are so many rules in methanol in industry, which is precursor to formaldehyde, acetic acid, and biodiesel.
Okay, so this is the reason of why PBR is selected. So the first point is PBR operates continuously. So this will enable the steady-state production of methanol in order for us to meet the large-scale industrial demand. This is why continuous operation is more preferred as compared to batch process. This synthesis also need a catalyst to allow excellent contact of gas-phase reactant and the solid catalyst to lead to high conversion efficiency and low catalyst loss. So PBR is well suited for operating at high pressure because it has no complex moving parts or any steering mechanism inside the PBR. So this also has efficient heat management, where cooler and heat exchanger will be integrated to stabilize the overall production temperature. This is the PFD of the whole process. So both of the reactants, carbon dioxide and hydrogen, will come out from its own storage tank. So both pipeline will go through inside the compressor, the first supporting units. So they need to be compressed from 1 bar to 70 bar, which is the required pressure inside the PBR. And then they will go through the heat exchanger. They will be exchanging heat with the water vapor, come out from the boiler. So they will be heated up from normal temperature to 523 Kelvin, which is the optimum temperature required inside the PBR. So by the time they're going through inside the PBR, there will be a chemical reaction inside the PBR, and then inside the PBR we'll be using the process of quasi-isothermal, where only small rise near the inlet and nearly flat temperature with slight variation across the reaction, because we acknowledge that this specific synthesis is isothermic reaction. So this will be helped by the internal cooling tubes that already implemented inside the PBR. So they will be maintaining the optimum temperature, 523 Kelvin, and then it will protect the catalyst. So this will be avoiding any temperature spikes across the reaction. So we will maintain high selectivity for methanol. So after that, the products will be going through PCV, pressure control valve, because they need to be reduced from 70 bar to 1 bar, and then the products need to be cooled down from 520 Kelvin to the normal temperature before entering the DC distillation column. So inside the DC, the temperature that we'll be using is the boiling point temperature of the methanol. So technically, we're going to get the top stream is methanol, the bottom stream is water. So the methanol will go through inside the second cooler, because they need to be cooled down before we store it in the storage tank, while the bottom stream, this the water, will be recycled back and then will be used in the boiler to go through inside the heat exchanger. So this is the PFD.
Okay, so for the AutoCAD, the green one is distillation column, and the brown one is heat exchanger, the red one is the compressor, the white one and in cone shape is cooling tower, the purple one is control pressure valve, and the last one, the cylinder one, is storage tank.
Okay, so this is a synthesis route. So first, 1 CO2 plus 3 H2 will produce 1 CH3OH plus 1 H2O, and the delta H is negative 49.5 kJ over mole. And as we know that this is exothermic reaction, so the catalyst is cuprum, zinc oxide, and aluminum oxide.
The key operating conditions is at 70 bar and 523 Kelvin, and the reaction step involve the adsorption of reactant on catalyst phase, hydrogenation of intermediates from methanol, and products dissolved from the catalyst phase. Next, for the calculation part, we are using MATLAB to calculate the conversion and also the yield of the methanol. In this part, we have distributed into 5 parts of analysis. Before we start, we have put the constant R equals to 0.08314 and K equals to 0.1, and we will let the users to key in their parameters such as the total pressure, temperature, flow rate for carbon dioxide and hydrogen, and also the concentration of carbon dioxide. For the first part of analysis, catalyst weight, we will let users to key in the parameters, and the result will come out with a graph which will be shown at the end of the calculation part. For the second part of the analysis, carbon dioxide feed molar flow rate. As mentioned before, using the same way, we will let users to key in their parameters and the result will be come out with the graph. For the third part of the analysis, carbon dioxide feed concentration, we will also let the users to key in their parameters and the result will be come out with a graph that will be mentioned at the end of the calculation part.
For the analysis of temperature, first we will let the user to input the temperature they like. After that, using the formula in the code, we will get the answer of methanol yield, and after that, a graph of methanol yield versus reaction temperature will plot. Same as the analysis of pressure, we will let the user to input their pressure they like. After that, using the formula in the coding, they will get answer of the methanol yield and a graph of methanol yield versus reaction pressure will be plotted. From the first graph, we noted when catalyst weight increased, methanol yield also will increase because that when the catalyst weight increase, more time to react over the surface, and when the lower CO2 flow rate reduce residence time and the concentration availability will be greater. So from the second graph, we know that when the pressure increase, methanol yield also increase. As we know that the temperature higher, reaction kinetic will be higher. So also for pressure higher, according to Leclerc principle, increasing pressure will increase the equilibrium toward methanol formation.
This is the part of SDGs, Sustainable Development Goals. So first, SDG 7 is about affordable and clean energy. So the hydrogen, one of our reactants, will be produced from the process of water electrolysis, which is powered by renewable energy. So this will promote the shift from using fossil fuel to clean energy source. So the methanol that we'll be producing can be blended into conventional fuel in order for us to reduce carbon emission into the atmosphere. So we will strive for a better and cleaner transportation and energy system. And next, SDG 9 is about industry innovation infrastructure. So we are planning to turn the waste into valuable feedstock by capturing carbon dioxide from industrial emissions. So eventually, this will support the industrial decarbonization by reducing carbon dioxide footprint.
So for SDG 12, which is responsible consumption and production, the first one, turning waste to wealth, because we convert carbon dioxide into ethanol. Next, sustainable chemical production, which is reduce or eliminate pollution at the source, unlike technologies and processes that target existing pollutant in the environment. And lastly, resource efficiency, because we using the earth limited resource in a sustainable manner while minimizing impact on the environment. So for SDG 13, which is climate action, the first one is reduction in greenhouse gas emission because we use the carbon dioxide. Next, decarbonization of industries, because the electrification of process heat using induction, radiative heating or advanced heat pump. And lastly, alignment with carbon neutrality goal, because having a balance between emitting carbon and absorbing carbon from the atmosphere in carbon sink.